This is Dr. Shankaraiah from Department of Physics. So in last presentations I have discussed about the theoretical part of module 1, and today I will discuss about the numerical problems of module 1. So the first numerical problem in module 1, which is crystal structure, says calculate the number of atoms per unit cell of a metal with lattice parameter 2.9 angstroms, given molecular weight 55.85 kg per meter cube, density is 7870 kg per meter cube, and Avogadro number is 6.02 into 10 power 26 kilo per mole. Okay, so this is per kilomole, that is why it is 26 instead of 23. So first, always we have to start with given. What is given in this problem? First, they have given lattice parameter A, which is 2.9 angstroms. So convert these angstroms into meters. So 1 angstrom is 10 power minus 1 angstrom is 10 power minus 10 meters, or 10 power minus 8 centimeters. So we are writing in meters. So 10 power minus 8 meters. So 2.9 angstroms is converted into 2.9 into 10 power minus 10 meters. And molecular weight M is 55.85 kg per meter cube. Density is given 7870 kg per meter cube. Okay, and the Avogadro number is, we already know Avogadro number, so 6.023 into 10 power 23, but here 26 per kilomole. Okay, 26 per kilomole. And we have already derived the equation for lattice parameter in terms of density, right? We have derived the equation for density, so we can write down the lattice parameter in terms of density. So the lattice parameter in terms of density, A is equal to N, or we can use this instead of small n, we can use this as Zm by rho into Na power 1 by 2. So if you write it in terms of rows, that will be A cube Na by Z into M is equal to 1 by rho, or rho is equal to Z into M by Na is Avogadro number into V is volume, which is Z into M by Na into V cube. So this is density in terms of number of atoms per unit cell, molecular weight, Avogadro number, and volume. This is V, not V cube, this is A cube. Okay, so we can, using this density formula, you can write for lattice parameter A is equal to Zm by a rho into Na power 1 by 3. Okay, so we are going to substitute. So what we have to calculate the number of atoms per unit cell. So that is Z, right? So we are going to calculate Z from this equation. So Z will be, from this equation, Z will be rho into Na into A cube by M. So rho into Na into A cube by M. So this is number of atoms per unit cell, which is Z. You can use small n also, but there will be confusion. So avoid confusion. So write it as Z. Okay. So now we have to substitute all the values of rho. Okay, rho density is given 7870, and Avogadro number is given 6.023 into 10 power 26. Because per kilomole, and A is A is given lattice constant. A is 2.9 angstroms, or 2.9 into 10 power minus 10, and divided by molecular weight 55.85. So substitute all the values, and then we will find out the number of atoms per unit cell is 2.06. To round it off, it is. So number of atoms per unit cell Z is 2. So the given lattice is a BCC lattice, because the number of atoms per unit cell is 2 for body centered cubic unit cell, or BCC unit cell. BCC lattice. Okay. So given lattice parameter, molecular weight, density, and the Avogadro number, how to calculate the number of atoms per unit cell, which is Z. So for that, we have used the formula, density formula. Density formula we have derived in the, when I am discussing about the theoretical part of module 1, I have discussed how we calculated this rho density, which is Z into M by Na into A cube. Z is number of atoms per unit cell. That is what we need to calculate in this problem. And M is molecular weight, Na is Avogadro number, and A cube is volume. Okay. So from this equation we need Z. So Z is equal to rho into Na into A cube by M. So substituting all the values in the formula, we got Z, the number of atoms per unit cell is 2. So from that we know that the number of atoms per unit cell is 2 for a body centered cubic lattice or unit cell. So this is the first problem in module 1, which is crystal structures. The second one. So chromium has BCC structure. Its atomic radius is 0.1249 nanometers. Calculate the free volume per unit cell. So they have given chromium which has BCC structure, and they have given radius, atomic radius is 0.1249 nanometers. So we have to calculate free volume per unit cell. Okay. So first always start with given. So whatever is given. So first they have given atomic radius R, which is 0.1249 nanometers, and free volume per unit cell. So that is what we have to calculate. And here free volume per unit cell here is 0.32 into A cube. Okay. So because we know that for BCC, the cracking fraction, what is the cracking fraction for BCC? 0.68, right? So 0.68, so 0.68 is the cracking fraction, atomic cracking fraction for BCC is 0.68. So that is for BCC. For a simple cubic, it is 0.52. So for the BCC, it is 0.68. So we have to calculate free volume. So that is 1 minus, so free volume is our void space, percentage of void space or free volume. Okay, free volume is atomic cracking fraction, and free volume for BCC. Free volume is 1 minus 0.68. So that is 0.32. Okay, and volume is A cube. So whatever is free, we are going to multiply. So 0.32 A cube. So this is the free volume in a BCC unit cell. Okay, so first we need to calculate A, and then we can substitute in the equation to calculate the free volume per unit cell. So we know the relation between R and A for BCC. So R and A, the relation between R and A is equal to 4R by square root 3, or R is equal to square root 3A by 4. Okay. So using this relation, we can calculate A. So A is equal to 4R by square root 3. So 4R is given as 0.1249 nanometers. 1 nanometer is equal to 10 power minus 9 meters. 10 power minus 9 meters. So 0.12 you can write as 0.12 into 1249 into 10 power minus 9. So 4 into A, 4 into R divided by square root 3. So we will get the value of A. First we will get the lattice constant A, which is 2.884 into 10 power minus 10 meters. Once we get the lattice constant A using the relation between radius and lattice constant or lattice parameter, then we are going to substitute in the free volume equation, so which is 0.32 A cube. So A is given, so we are substituting this equation 0.32 into A cube. Okay, so finally we end up with 7.676 into 10 power minus 30 meter cube. Okay, so this is finding out the free volume in a given unit cell. So first we know the percentage of void space in every unit cell, at least in BCC, simple cubic, BCC and FCC, right? So for a BCC unit cell, the atomic cracking fraction we know 0.68. So 1 minus 0.68 is the percentage of void space, right? So that is 0.3. Instead of percentage, if you write the fraction, that is 0.32, and that is the space that is available as free. Okay, so we want the volume of free space. So that is volume is A cube, because each axial length. So this is a cubic lattice. A is equal to B is equal to C. That is why volume is A cube. Okay, 0.32 into A cube. So you will find out the free space, volume of the free space in a BCC unit cell. Okay, so this is the second numerical. Coming to the third one. So copper has FCC structure and atomic radius is 1.278 angstroms. Calculate the density of copper crystal given atomic weight of copper is 63.5. Okay. So they have given the atomic weight as well as density of copper crystal. We have to calculate the density of the crystal. They have given atomic radius. So first start with given. atomic radius which is 1.278 angstroms, atomic weight which is 63.5. Now the relation between R and A again, okay, for FCC, R and the relation between R and A is R is equal to A by 2 square root 2. Okay, so the radius of this FCC unit cell radius is R is equal to A by 2 root 2. So we need to calculate A. So we need to calculate A. So from this equation, A is equal to R into 2 root. So R is given 1.278 angstrom. So convert that into meters and then finally we end up with 3.614. Okay. So that is A. Avogadro number we know. So then substitute in the equation of density. So from the relation between atomic lattice constant and density equation, so this is Z. So obtain the equation for density. Density is Z into M by Na into A cube. A cube is the volume. So we know this is a FCC structure. So Z is 4. For a FCC structure, Z, the number of atoms per unit cell is 4. So 4 into M, molecular weight they have given, 4 into M divided by Na, we know A is obtained. So substitute all the values, we are going to find out the density which is 8.92 into 10 power 3 kg per meter. Okay. So here they have given atomic radius as well as the molecular weight. So using that we have to know the number of atoms per unit cell for a cubic FCC unit cell which is 4. So number of atoms per unit cell for FCC is 4. And then the relation between atomic radius and lattice constant which is R is equal to A by 2 root. Okay. Using these two relations, we will first find out the lattice constant A and then substitute that in the relation of density and lattice constant to find out the equation for density and then substitute the values, we get the density of copper. So the fourth numerical problem in module 1 is show that in a simple cubic lattice, the separation between successive lattice planes is the planes are 100, 110, 111 are in the ratio of 1:0.71:0.58. Okay. So we have to show that for a simple cubic lattice, the separation, the interplanar spacing between these given planes is in this ratio. Okay. First, the equation for the interplanar spacing we have derived, that is D is equal to A by square root H square plus K square plus L square, where H, K, L are the Miller indices, right? Right. So first plane D110. So these are the Miller indices of this plane. So 100. So D100 is A, right? A by square root 1 square plus H square. H is 1. So this is HKL. HKL for this plane. HKL for this. So for this plane A, the interplanar spacing is A. For the second plane, interplanar spacing A by square root 2. The third plane, interplanar spacing is A by square root 2. Okay. So if you write these in the ratio of D 100, 110 and 111, the ratio will be 1:1 by square root 2 is to 1 by square root 3. Because A is common, then so 1 by square root is 0.7 and 1 by square root 3 is 0.57758. Okay. So if we know the relation or equation for the interplanar spacing, then using the equation for interplanar spacing, the planes are given. The Miller indices of each plane is given. So substitute the values of HKL, you will find out interplanar spacing and write them in the ratio. You will find that whatever they want to show, they ask us to show, is what we get. So the fifth problem, find the Miller indices of a set of parallel planes which makes intercepts in the ratio 3a:4b on the xy axis and are parallel to z axis. ABC being primitive vectors of the lattice. So we have to find the Miller indices of a set of parallel planes which makes intercepts in the ratio of 3a:4b and it is parallel to z axis. Okay. So first always start with given. So intercepts are given 3a and 4b. Okay. And z axis is parallel to z axis. So the intercept is infinite. Okay. So PQR. Okay, so PQR 3a:4b is infinite. So these are the intercept. Then we have to write the reciprocals, right? So the reciprocals of intercepts are 1 by, okay, so 3a:4b, right? So 1 by p, yeah. So first write the reciprocals. So the reciprocals are 1 by p is 1 by 3, and 1 by q is 1 by 4 and 1 by infinite is 0. Then because there are fractions, we need to multiply with the least common denominator, so that is 4. So when we multiply with the least common denominator, so for the first one we get 4, the second one we get 3, and the third one 0. So okay, so these are the HKL, Miller indices. Okay, so the Miller indices are 4, 3. So you should not write Miller indices separated by commas. So you should write Miller indices as 4, 3, 0. Okay, so these are the Miller indices of the given plane, which are 4, 3, 0. Okay, we have discussed the steps to find out the Miller indices, right? First, write down the intercepts. Once we write down the intercepts, write the reciprocals of the intercepts. Once you write the reciprocals of the intercepts, there are any fractions in the reciprocals of the intercepts, multiply with least common denominator. Once you multiply with the least common denominator, you put them in parentheses without any commas. So those are the Miller indices. Okay. The sixth problem. In a triclinic crystal, a lattice plane makes intercepts of lengths a comma 2b and minus 3c by 2. Okay. Find the Miller indices of the plane. They have given that it is a triclinic crystal and lattice plane makes intercepts a comma 2b comma minus 3c by 2. We have to find the Miller indices. Again, start with the given. Given the intercepts are a comma 2b comma minus 3c by 2. So a 1 comma 2 comma minus 3 by 2. Now write the reciprocals. Okay, a comma 2 comma minus 3 by 2. Write the reciprocals, which are 1 by 1, 1 by. Okay, reciprocals are 1 by 1, 1 by 2, minus 2 by 3. So because there are fractions, we need to multiply with least common denominator. So that will be, so that is 6. So 6, 6, 3 and minus 4, because 6 ones are 6 and here 2 3s are 6. So 3, and already there is a 6. So 3 2s are 6. So 2 into 2 minus. So that is minus 6, 3, 4. Whenever there is a minus 4, then we have to put a bar on that same, right? So that is 6 comma 3 comma 4 bar. So no commas here, right? So no commas for Miller indices. So given the first given the intercepts, always you need to write the reciprocals. Once you write the reciprocals, if there are any fractions, multiply with the least common denominator, right? So then after multiplying the least common denominator, you are going to get integers. So put them in parentheses without commas. So those are the Miller indices. If you have any negative sign in front of any Miller indices, put a bar on the same integer, removing the negative sign. Okay. So here there is minus 4. So what I have done, I have put a bar on 4, removing minus sign. Okay. So these are the Miller indices for the given plane. Seventh numerical problem. Determine the spacing between 100 planes, 110 planes and 111 planes in a NaCl crystal having the lattice constant A is equal to 5.64 angstroms. Okay, so so we have to find the spacing between these planes. They have given the lattice constant. Okay, so that determine the spacing. So we have to calculate the interplanar spacings between the planes. So Miller indices are given as 100, 110, 111. Okay, so this is the interplanar spacing relation. So using this relation, we can find out the interplanar spacing for all the planes, right? So these are HKL 100. So these are the HKL values. Okay, so for the first one, it is 5.64 angstroms, 3.988 angstroms, and 3.256 angstroms. So these are the Miller indices given. We have calculated the interplanar spacing for the given planes 100, 110, and 111 planes. Okay. Eighth problem. The distance between 110 planes in BCC is 0.203. nanometers. Calculate the size of the unit cell and radius of atom. So start with given. Miller radius is given 100 and D interplanar spacing is given 0.203 nanometers. So the relation between interplanar spacing, the relation for interplanar spacing is, the equation for interplanar spacing, a relation between D and A is D is equal to A by square root H square plus K square L square. From this equation you can write the equation for A, so that is D into square root H square plus L square plus K square, right? So substitute H, K, L and D, then you will find out A. Once you find out A, then you can calculate the radius, the relation between radius and atomic constant, radius and lattice parameter. Using that relation between radius and lattice constant, you can find out R. Okay, so once we find out the radius, okay, so they have asked us to find out the radius of the atom. So the relation between R and A is given for the this. So we are taking, so R is equal to square root. So yeah, so square root 3A by 4. Okay, so A is calculated from this interplanar spacing equation. Substitute A in square root 3A by 4. So then you will find out radius. Okay, so radius of the atom is evaluated. Then we have calculated the size of the unit cell. So size of the unit cell is nothing but the volume of the unit cell. So volume of the unit cell is A cube. So we already know what is A, right? So already know what is A. So then put it in the equation. We will calculate volume of the unit cell or size of the units. So a copper has FCC structure with atomic radius 0.1278 nanometers. Calculate the interplanar spacing for 111 and 321 planes. Okay. So FCC structure, we have to calculate the interplanar spacing. Start with given, atomic radius is given, and FCC structure they have mentioned. So for the FCC structure, the relation between R and A is R is equal to A by 2 root 2. So we know A. Did they give A? No, they have not given A, but they have given R atomic radius. So A is equal to R into 2 root 2. So you calculate A. Once you calculate A, right? So yeah, atomic radius is given. So we have this. Then substitute in the interplanar spacing equation, D is equal to A by square root H square plus K square plus L square. A is calculated already, right? So A is evaluated as 0.361. By substituting the value of R 0.1278 nanometers, we get A is equal to 0.361 nanometers. 1 nanometer is 10 power minus 9 meters, so that is 3.61 angstroms. Substitute the values in the equation for interplanar spacing, we will end up with different values for different planes. 0.2 nanometers for the 111 planes, 321 planes, it is 0.09 angstroms. Okay, so the last problem in module 1 is potassium chloride is a FCC crystal having a density of 1980 kg per meter cube. If its molecular weight is 74.6, calculate the distance from one atom to the next atom of the same kind and the distance between the adjacent atoms. So always start with given, density is given 1980 kg per meter cube, molecular weight is given, Avogadro number is known, FCC they have mentioned it as FCC, so Z is N, Z is number of atoms per unit cell is 4. So now we have to calculate the distance between the same kind of atoms. Okay, so the distance between the same kind of atom, to calculate that we are using this formula relation for between A and density, lattice constant and density. Using that we have calculated the equation for lattice constant, and the distance between the same atoms is A in the potassium chloride. The distance between the same atoms is A, which is 6.3 angstroms, and the distance between the adjacent atoms is A by 2. Okay. If you draw the FCC crystal, you will find out the distance between the same atoms, K, potassium or chlorine. The distance between the same atoms, it is A. If you write the FCC crystal, right, FCC crystal is something like this. So this is potassium and potassium, or chlorine, okay, or you can write chlorine here and chlorine here and potassium here. So the distance between the same type, okay, so potassium chloride. So the distance between the same kind, the distance between the same kind is A, and the distance between, yeah, so this is K, this is, sorry, so that is all K, potassium, and here it is chlorine. Okay, so the distance between the same kind is always A, and the distance between the adjacent atoms. So that is A by 2. So this is A by 2. So once you calculate A divided by 2, so that is what you will get. So A by 2 is the distance between the adjacent atoms. Okay, so these are some of the references which I have used. And so in this presentation, I have discussed about numerical problems in module 1. And in the next presentation, we will discuss with some other presentation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.